Hey kids, yet another face-to-face with me here because there's some things I definitely wanted to demonstrate for you to see. So again, because this video does not accompany a live session, I'm going to go ahead and do the warm-up as if we were in a live session. And this warm-up practices another volume by revolution. This is the last volume by revolution practice in one of these videos. We're going to move to volume by not revolution in this video. All right. I'm asking you to use the shell method. The shell method is a method of finding volume by revolution. It's just not discs or washers. So if you remember, shell method talks about taking the surface area of a cylinder, which is 2 pi times the radius times the height, and then multiplying times the width of those really thin cylinders to get volume. And of course, what you are integrating with respect to, whether this is x or y, determines what these numbers are. Determines what your height and your radius functions are or expressions are in terms of. So this one is one that you might have a calculator with, but you might be, because it's not, I don't expect that you know what this looks like, but I wanted to do this warm up because if I have my calculator, I can't plug in x equals, but I can plug in y equals and just pretend. Okay. So what you're going to get here, the bounded area, and also this means you need practice. If you just do a regular Zoom 6 window, this region will be so small, it'll be very difficult for you to see. So this region is between the y-axis, the x-axis, and y equals 1. But I want to rotate around the line. Oh, I didn't really leave a good enough space, did I, to draw? So notice I'm going to redraw because I'm going to be reflecting around the line y equals 2. So there's the y-axis, the x-axis, y equals 1. And then my axis of rotation is y equals 2. So I've taken care of my bounds, my line. Now I just have to graph this function. It is an e to the, so hopefully it's not too surprising what I look like. I guess I can still do this in red. So it does decrease, but it kind of has this curve right there. Okay, so the shape that I am going to spin looks like this, bounded by that curve and the axes and y equals 1. But I'm going to reflect it across. This is my axis of rotation. So my job, before I worry about shells or washers, my job is to draw the reflection. And I'm terrible at drawing reflections. Absolutely terrible. I'll do my best. Let's see. Here, here, right? And then what? Something like that. That's my image. Now, if you want to do shells, remember I know the shell formula is 2 pi times the radius times the height times d something. That's going to give me volume. Also, the other thing to remember about shells is that the strip you draw is parallel to the axis of rotation. Unlike discs and washers, where the strip that you draw needs to be perpendicular to the axis of rotation, I'm asking you to do shells. My axis of rotation is horizontal, so the strip I'm going to draw here is horizontal. Take a moment and look at that strip as I drag it up and down through the image. Notice that the right side and the left side do not jump boundaries, so I don't have to jump integrals. Now I draw the image of my strip. And this time with shells, remember what I do? Is create a cylinder. So there's that cylinder. The cylinder is on its side. It's really, really thin. And I'm going to draw, right? I can draw many other ones. I can draw another strip here, here, and I get these idea of these nestled shells, right? These nestled cylinders inside one another. Again, the Matryoshka dolls, if you will. So there's my cylinder. So now I just have to figure out in my formula, 2 pi is going to be on the outside. Since my strip is parallel to the axis of rotation but is pointing at the y-axis, I'm going to integrate dy. That's nice since my function is in terms of y. And now I just have to figure out what my radius and my height are in terms of y. And I have to figure out, hopefully you can see that I'm going to start my shells at 0 and end them where? At 1, right? So now let's go try to figure out the radius. The radius is always measured from the axis of rotation. So what's the radius of my cylinder? There's the axis of rotation all the way out to the edge of my cylinder. How long is that? That's my radius. Well, it is not 2. What is it? 2 is too much for the radius. Shrink it. Shrink it by how much? Whatever this y value is. Right? The minute you see that the line you're revolving about is not a 0, it's not an x-axis or y-axis, oh shit. You're going to have to shift your radius. Okay? Now, what is the height? The height of my cylinder goes from the y-axis out to this curve. What distance is that? It's an x distance, but that x distance changes as you go up and down through the, how do you describe that? The x distance is e to the negative y squared. Okay. So again, put that into your calculator, Math 9 that, give me an answer that is 3 places past the decimal. I keep forgetting to write these answers down. I really care that you can set it up. So shell method, 2 pi out front, because it is still a revolution, but you're revolving the strips, right? Instead of, right, you're revolving the strips and creating a cylinder. And that is all because the strip that you're rotating is parallel to the axis of rotation, as opposed to a strip that is pointing at the axis of rotation, right? And then when you spin your strip this way, you create the disc or the washer, right? This way, you create the shell, cylinder. All right, so this handout here that is part of your homework, I'm going to start in this video. So you want to access that handout if you want to take notes during this. The rest of these problems are in the book. Some of the problems in the book, again, are nice. Some of them aren't the best. The handout is a better representation of what you would see on AP. All right, so when I say known cross-sectional area, every cross-section you did with a solid of revolution was a circle or a cylinder. Now, the cross-sectional area might be a square. It might be a circle. It might be a semicircle. It might be a rectangle. It might be a triangle. Maybe it's a right triangle. Maybe it's an isosceles triangle. Maybe it is an equilateral triangle. Maybe it's a trapezoid, no, right? Those are your known cross-sectional areas. Remember, you need area to get to volume. So you do need to know, and AP won't give you this, you need to know the area formula for a square, the area formula for a circle, the area formula for a semicircle, the area formula for a rectangle, and the area formulas for triangles. No one is going to give you those. Okay? You took middle school geometry for a reason. Not a lot of reasons, but for one of these reasons. Because we are going to compute volume given the area of these geometric shapes. I call these Play-Doh problems. So that handout I referred to is going to have this function on it for a whole bunch of problems. Algebra 1, x squared plus 1, bounded by the y-axis, the x-axis, and the vertical line x equals 2. Here's the word that means Play-Doh to you. The region in the 2D plane is a base. So you're going to take your XY axis and you're going to lay it down on the floor, and we're going to build up from it, technically into the Z plane, but that's what we would do in multivariable. We're not going to deal with thinking about a whole other third dimension axes and multivariables. We're just going to build up with known cross-sectional areas, because I don't need that if when I'm building up with squares, or I'm building up with semicircles, or I'm building up with triangles. I know those area formulas, and I just have to sum them, multiply by thickness, and I get volume. So the reason we call these Play-Doh problems is because, now again, if we were in person, sadly, everybody would have, I'd have about 6 or 7 groups in the room, and everybody would have a little cute little thing of Play-Doh. Isn't that adorable? There's some Play-Doh. So where's my camera? Here is the shape described by my yellow highlighted information. X squared plus 1, bounded by the y-axis and the vertical line x equals 2, and the x-axis. Here is that same shape filled with Play-Doh. Do you see it? I just took Play-Doh out and I filled that shape in. It's not super, super great, but pretty good. The reason I want you to visualize this is because I'm going to take, this is my region. This is my bounded region. I'm going to lay it on the ground, and I'm going to take some shapes. See, there's a cut out of index paper. There's a little square. And I'm going to put the square in my Play-Doh. And then I'm going to put a smaller square. And then I'm going to put a bigger square. And I could do this an infinite amount of times. Well, physically, I guess I couldn't do it infinitely amount of times. But, so what I'm doing here is I'm just shimmying in those squares into the Play-Doh. And I'm going to give you with 3 little index card square things. Hopefully you can visualize, because I don't have time to do more. You see what I've done there? I don't know if you can tell what I've done, but I've put squares into the Play-Doh, into my shape, right? Do you see it? Can you imagine putting an infinite amount of squares in that shape? And then I would have a solid. right? I would have a solid, and it would be a three-dimensional solid whose base is the Play-Doh and whose height comes from differing heights of squares. So that's what we did here. This is number 1 on the handout. Everybody got Play-Doh. We filled the place, I just did it for you. Placed a square in the base. Now, I'm going to take the squares out. If I take the squares out, I want you to look at the image left in the Play-Doh. Can you see that line? Can you see the line left by the 3 strips? That line, each one of those lines represents what to the square? Right? The strip. Notice that the strip in the Play-Doh pointed at the x-axis. Pointed at the x-axis, right? The strip in the Play-Doh, because this is the way I put my squares. I put my squares perpendicular to the x-axis, and that's what this says. Perpendicular to the x-axis, which means my strips are pointing at the x-axis, which means I'm going to integrate dx. What is the area of one single one? Side squared, right? So how can you write an expression using the yellow information for the side of one square and then the side of another square, the smaller one, and the size of the smaller one? What can you do? Right? The length of each side of those squares is the distance from the x-axis to the function. X squared plus 1 is the length of one side. So each square, this was the side strip in the Play-Doh. The strip was perpendicular to the x-axis. Therefore, I'm integrating dx. The area of a square is the length of its side squared, right? That's how you find the area of any square. So I am going to sum all the squares, the length of its side squared. Notice there's no pi in front or 2 pi in front because I'm not revolving. I'm not revolving. I'm building up from a base. That's what I get. I could start building squares at 0, 0, and I could put an infinite amount of squares in here until the boundary of 2. That's where these numbers came from. My strips were parallel to the x-axis, which is why I'm integrating dx. And x squared plus 1 was the length of the side, the length of the strip. Okay, pretty cool. That's a Play-Doh problem. You just did number 1 on the handout. So this is the formula in general. If you have volume of a solid whose known cross-sectional area is area in terms of x, right? So I know the area of the square is side squared, but I wrote my side in terms of x. When we have volumes of a solid where the region that's described to me is the base. The region given to me isn't being spun anywhere. It's being laid on the floor and used to build up from. This is the volume formula. So imagine this is the x-axis. Look at all these squares. Each strip in the Play-Doh I guess that's not a great picture, is it? Because both of those sides, this is, right? Not the best picture. Sorry. This should be A of y. That's if the known that's if the R is the base, the region is the base. But the strip in the Play-Doh points to the y-axis. Or when they tell you to lay the cross-sectional pieces are perpendicular to the y-axis. They will always tell you, lay it perpendicular to the x-axis or lay your shape perpendicular to the y-axis. They will always give you that information. So here's number 2 on the handout. Notice that everything is the same. Same shape, same boundaries. The region described to me is going to be not spun or revolved or rotated. It's going to be used as a base. The cross sections are perpendicular to the x-axis. However, what is my shape? I don't know why I guess I have my email open. Sorry for the ding, ding, dings. All right. Semicircles where, be careful, watch out. The diameter lies in the Play-Doh. So, how do I start this problem? Right? The area of a semicircle is pi. The pi isn't there because I'm spinning like it is with dishwashers and shells. The pi is there because my shape that I'm building with is a semicircle. So pi r squared cut in half. And I'm going to sum all of those up. Since I'm perpendicular to the x-axis, I'm going to integrate with respect to x. These numbers are going to be x numbers, and my radius has to be in terms of x. So I didn't make 3 of those. I only made 1. Here is my really pathetic semicircle. No judging. But look what happens when I lay one semicircle in the Play-Doh. Right? There's one semicircle in the Play-Doh. Imagine putting an infinite amount of semicircles in there. Right? An infinite. It would be a solid, but instead of the top being right square, right, it would be smoothed, almost like one of those Thanksgiving, what are they called? Like cornucopia things, right? But when you take the semicircle out, look at the strip in the Play-Doh. It's pointing at the x-axis, which we expected. I get it. The length of this strip is x squared plus 1, no matter where I put my semicircle. But what is x squared plus 1? Is it the radius? No, honey, it's the diameter. So be careful. I'm going to fill in 1/2. I'm going to fill in pi. I'm still going from 0 to 2. Do not square the diameter. Square, the radius. I have the diameter. The diameter is equal to x squared plus 1. So there is the diameter in terms of x. If you have a diameter, how do you go to a radius? The diameter has to be divided by 2. So you can integrate like that, or you can square this 2 and get 4. Osmosis that 4 out. If you had to do this by hand, you would multiply that out. Can't do use substitution because there's no x available, but you can square that out and then do your individual, or you just put this in Math 9. Okay, but this is the most common mistake when kids have a semicircle problem. They forget, they use the radius. I'm sorry, they use the diameter instead of the radius. All right, next shape. Triangle. This is number 3 on your handout. right? If you look at your handout, this is number 3, where same shape, same boundaries. The region is being used as a base. The region is not being revolved anywhere. I'm going to put shapes in my Play-Doh that are perpendicular to the x-axis. But this time, I have a triangle whose base and height are equal. And the base is lying in the Play-Doh. So, triangle. What's the area of a triangle? 1/2 base times height. That's more than one situation. But what did they tell me? The base and the height are equal. Who's in the Play-Doh though? Who's laying in the Play-Doh? What's your strip? When you put your shape in when you put your triangle into the Play-Doh, it's hard to do this, right? Into the Play-Doh, who's pointing at the x-axis? The base, right? So my base is described by x squared plus 1, but what do they tell me about the height? It's equal to the base. So sum all of those triangles up. 1/2 base times height, but the base was the same in this particular problem, and that's how I'll get my volume. Start putting rectangles in Play-Doh at 0, stop at 2. The base is x squared plus 1 squared, pointing at the x-axis, so I'm dx. I did write down answers for these. The first one with squares, the answer with squares, I just found my work. 206 over 15. The answer with semicircles was 206 over 120 pi. And this one was 206 over 30. Right? That shouldn't be too much of a surprise, right? Because this was x plus 1 squared. Whoops, sorry, the square was. Sorry, not the semicircle. Right, there's, because I had 8. All right, so not too bad. Now this one, is this on your handout? No, this one's not on your handout, but I wanted to show you that you might need some special triangle memory relationships. So this time I have an equilateral triangle with one side. Doesn't matter which side, right? They're all equal. So you do need to remember, to be honest, you need to remember for our test, not for AP. You do need to remember some situations with an equilateral triangle that your altitude bisects your base, bisects the angle, the vertex angle where you draw the altitude from, meaning this angle used to be 60, but now it's 30. This is 60. This is 30. So I'm just going to give you the triangle trig relationship here. If you have an equilateral triangle, √3 times the base is the same as the height. Okay? And that just comes from solving for this h with Pythagoras. Come on in, Pythagoras. Pythagoras, right? And some triangle trig. And what I want to do is, if I put this strip into the Play-Doh, I have an equation, x squared plus 1 gives me that strip in the Play-Doh. So I wanted to get the height in terms of the base. And with an equilateral triangle, the height is √3 over 2 times the base. So I multiplied the 1/2 and the √3/2, and I got √3/4. I would osmosis that out. Whoops, sorry. Come on, pen. Calculator's thinking. I mean, my computer's thinking. Blah, 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 blah. My pen froze. The answer to this is 206/5. Right? 5, yes. There we go. Still triangles from 0 to 2. In the Play-Doh is the base. The base gets squared, right? Do you see why that is? I rewrote the height in terms of the base. Oh, wait, no, sorry, that's a problem. This problem's not on the handout. I'm giving you an answer from the handout, so I don't know. I didn't write this one down. My apologies. Let me make sure that I didn't write it down anywhere. No. Also not on the handout. These are like a couple of your book problems. Don't see this too much on AP, but I want to make sure that you know that just because I don't have to stop, right? If I take this square and put it in the Play-Doh, I just laid it in the Play-Doh, but I could go through the paper, right? It's hard for me to demonstrate with this piece of paper. I really challenge to draw it, but I'll try. So we have a region in 2D. 2D, that's the XY plane. My functions are plus and minus 2√x, going from 0 to 14, right? The y-axis and the vertical line, x equals 14. And then 2√x is the top half of a sideways parabola, and negative 2√x is the bottom half of a sideways parabola. So that's my Play-Doh. Imagine taking your Play-Doh, isn't that awesome? I love when I freeze and like my face is like this. Take your Play-Doh, fill in your base. I am using squares this time. I am using a square. This is more like a rectangle, but you get it. A square, but the diagonal right? The diagonal of the square is laying in the Play-Doh. So for the diagonal of the square, can you see that? I drew there you go. The diagonal to lay in the Play-Doh, this part of the square has to go down through, the Play-Doh. So it's part of, right? So the top half of the square, top, right, triangle piece of the square, it looks like a triangle up here. And then underneath of the Play-Doh, you have the other half of the triangle. And this is the diagonal of the square. No, I didn't do a good job of making that perpendicular to the x-axis now, did I? There's the diagonal. There's the top half of that square. It looks like a triangle, but the other part of the triangle is below the Play-Doh, right? It's going down into the ground. So when I'm doing this, I know how to find the area of a square, right? The area of a square never changes, but the problem is, who's in the Play-Doh? Is the side of a square in the Play-Doh? I don't think so. In the Play-Doh, My strip, which is perpendicular to the x-axis, is the diagonal of a square. Come on. Why, when I'm doing a video, does this choose to get choppy? Diagonal. That doesn't help me when I'm trying to sum the area of a square. The area of a square doesn't change. It's the side, not the freaking diagonal. So the question is, do you remember how to get from the diagonal to the sides of a square? Oh, I forgot that I drew I forgot I had a picture there. The x-axis goes through the middle. So you need to see, this is the Z plane. I captured this picture from a 3D, right? So you need to think about, this is the x-axis, this is the y-axis. This has been laid down on the floor, right? Here is the diagonal of the square. The diagonal of the square goes, right? Don't forget that in 2D, what this looked like. Looked like that in 2D, where the diagonal of the square is perpendicular to the x-axis. How long is it? How long is that? Well, it's 2 root x long this way, and it is 2 root x long this way. So how long is the diagonal in toto? Again, that's swell. Yay, sort of, because I need to sum the area of the square, which is side squared. I'm going from 0 all the way out to what? Do you remember? 14. All right. Let me draw. Here's the diagonal. I'm just drawing the top half. What do you know about a square? This is a side of a square, and this is a side of a square. What's true about those? They are the same, right? Side 1 is equal to side 2. Further, what do you know about the angles of a square? So that is really a 45-45. 90. Right? Where you know that the diagonal is 4 root x. How do you go from the diagonal? How do you go from the diagonal of an isosceles right triangle back to the legs? Pythag! You always take the hypotenuse and divide it by root 2. OMG. That high school geometry was good for a little bit of something. All right, let me get all this mess off of here. So what do I want to do? The volume is the sum from 0 to 14 of the length of those sides squared, dx. I had the diagonal, which is 4 root x, is what's in my Play-Doh to get from the diagonal to the side of that rectangle, squared, divide by root 2. So if you clean that up a little bit, right, this is going to be 16 root x over 2, which is 8 root x. Osmosis the 8 out. Oh, sorry, x, right? If I squared it, it's not square root anymore. And that's a very simple integral to do by hand. Right? Try another one like that before we go. Okay, this time, same situation, different shape, but the region is a base, that's Play-Doh. The cross sections are perpendicular to the x-axis, that's dx. I'm dealing with squares, side squared, but the diagonal is lying in the Play-Doh. So it's just like this, except my boundary is different. Five times the square root of x is just a diluted, like that. 2 root x looks like that. I'm going to put I'm going to put strips in the Play-Doh. Lay Play-Doh on here. Take the XY plane and lay it down on the ground. Right? Take that 2D shape, lay it on the ground, fill it with Play-Doh, put squares through it, not just in it, through it, so that the diagonal of the square is in the Play-Doh, but that's just like this scenario. It's just that my boundary is different. Right? So I need to sum side squared dx. Dx comes from perpendicular to the x-axis. Side squared comes from the idea that I'm dealing with squares. But to get an expression for the side in terms of x, what is the length of this strip? It's not just 5 root x, is it? How do you go from the diagonal to the side of a square? There you go. You need to find this place of intersection, use your calculator. This point of intersection, use your calculator. Okay, I trust that you can do that. I wanted to do 2 examples where the diagonal of a square is in the Play-Doh. Okay, so the handout again does a lot of practice with this shape still, right? Our x squared plus 1 shape. And I try to give you a hint which one on there. I put icons on the handout. Do this without a calculator. That's just to practice your integration. You, of course, don't have to on homework do it without your calculator, but you are going to be asked to integrate with these problems sometimes by either us or AP. But the integration wouldn't be like this one, 5 root x minus 2 to the x over root 2. Okay, it would be x squared plus 1. All right. I will see you in our next live session. Bye.